Let's go ahead and get started. So, after last class, it became a little obvious that not only are you continuously talking a lot, that, oh, Colorado, nice. All right, that we had some confusion about the jump from going from our essentially, what was it, finite state machine, our non-programmable controller, to an actual programmable controller. And that jump was a little confusing, and I get that. So today I'm going to start, I'm not going to go through it all, but I'm going to go start basically coming from the other direction. Namely, instead of asking, hey, we started with transistors, how do we build up to a computer? I'm going to say, well, right now we have C. How do we go from C to executing on this machine that we have? So you see I'm going basically top down now instead of bottom up. And maybe we can kind of converge on the middle and it'll make a little more sense about what's going on. So this class we're going to do x86 assembly. We might, sometimes we'll do 32-bit, sometimes we'll do 64-bit. Unfortunately, they're both confusing, so sorry. So what's next? Okay, wow, let me just rephrase this. We did the finite state machine. How can we make it programmable? There are so many options out there that it's obnoxious. So instead of trying to develop one way or learn how we did it historically, we're just going to watch what happens. What does GCC do, right? We'll just look at GCC, how it works, and then go from there. Keep in mind that what GCC does for C, basically every language that you use has to do this at some point. It has to translate your language to what can be executed on your machine. So let's start with our good Hello World program. Hey, there it is.
Hello world.
Good old Hello World. Let's see. I think I actually started this.
This is C, right? Not
Nope.
C++ or whatever.
Right. We don't need any of that silliness. It's class code. There we go. C to assembly. All right. Oh yeah, there it is. Hello.c. So int main. Good. You sure you should read that. Int main, print hello world, and then get out. All right, very simple. Hopefully y'all wrote this in procedural. Okay, you can tell GCC to, instead of doing everything for you magically and nicely and make it happen, to actually do individual steps. One step you can do is convert your C program to assembly. By the way, by the official standard definition of a compiler, all a compiler does is take your C code and convert it to assembly. It doesn't do everything else, anything else. It just happens that GCC is nice and does the rest for you. So how do we do that? Well, -s means convert to assembly. This -m and then -m is a flag, and you're saying set ASM equal to Intel. You're telling it to use the Intel syntax for x86 assembly, and -m32 says make it 32-bit assembly. Okay, let's go over there and do that. GCC -s MASM, what was it, equals Intel -m32, we have hello.c. All right, and now we should have a hello.s file. Let's go ahead and open that up. Alrighty then. So what the compiler did, or what the C compiler does, is translate your C code to this. All right, well, everyone got this? Nailed it? All right, well, hopefully at least parts of this make some sense. Hey, look, there's a string. It says hello world. We typed that in. Okay, good. Sure, I don't know what that is, or you probably don't. Main, hey, I typed in main. And sure, it's a function. Great. Why do we have main down here? All right, fine, whatever. Leia? What's Leia doing here? Now, anyways, so what's happening with these instructions, the top part is basically the setup. That's the A. Wow. This projector is cutting it. All right, so let's go and do this. There. So when I was saying main, I was saying this, not AIN colon. That would have been weird. All right, ignore these dots. When you ever see something that starts with a dot, it's usually some type of description inside of assembly. We're going to ignore that for now. And then we go for LEA, less than or equal address. It's an instruction. It's saying you grab less than equal or address, so you're doing the address based on the ESP. What's ESP? No one knows what ESP? They don't do.
How would you guess? It's a register.
It's a register. Good. Well, that's what it is here.
External service provider?
Oh, you're close.
External?
External sensory perception. Oh, so close. No, it's no. That was a lie. It's the extended stack pointer. Sorry.
So I wasn't close?
No, you're right, Xavier. Extended stack pointer. What does that mean? Well, it's a stack pointer. E stands for its 32-bit because x86 was originally 16-bit, so the E is for the 32-bit one. The 64-bit one is R, whatever. Anyways, the colon means grab the information in that register and then multiply it by 4, and whatever that is, compare it to what's inside the ECX register, and then set the flag if it's less than or equal to it. Okay. Well, that's kind of weird. I mean, not weird, but that's a lot. Hey, look, and. We talked about and. We're going to do the binary and of the ESP and -16. And then store that back in ESP. We haven't talked about push, but if you look, there's a lot of pushing. And then down here, there's a lot of popping. What does that sound like?
A stack.
A stack. So there is a stack in here. Good morning. And there's a bunch of other instructions. Hey, look, we're going to add EAX to, oh, what is all that? All right, so this is kind of confusing, which I get. And what GCC spits out is confusing because it's auto-generated. You probably have seen like auto-generated HTML or PHP. It's not very human readable, which is why this is not human readable. But we're going to get to at least be able to write our own. But anyways, we have the assembly file. Well, that's nice. Look at it. Kind of confusing. All right. Now you can link it. You can call GCC again. Notice that, that was the assembly. Did I miss a step? Oh, I totally missed a step. Good thing I wrote it down in the makefile. So we call AS, aka the assembler. We say its output is hello.o, and we're going to call it from hello.s. Oh, it did not like that. Because it's 32-bit assembly and it wants 64-bit. So hello.o and then hello.s. All right, if we do an ls, there's hello.o. Does that look familiar, guys? That is the object file that it creates. If I do a file on hello.o, it's going to be hard for y'all to see, so let me clear. File hello.o. It tells you that it's an elf. Ooh, what's elf?
Santa's
Really?
helper.
It's a Santa's helper. Great. Okay. Any others?
I'll say elevated. No, that's not right.
Elevated. I like that.
Yeah, no, never mind. I was going to move them.
No one's going to do Lord of the Rings? Or D&D/Norse mythology? No? Okay.
I figured that wasn't really the answer, so I wasn't going to say it.
I'll say, what do you want to hear? Is it Legolas?
Yeah, there you go. Okay. Good guess. No, it's the extended Linux format. So it is a container format about how you contain the machine code. 64-bit. Okay, great. Ooh, LSB. We'll just skip that for now. 64 version 1, System 5, System V. We all remember System V growing up on all of our machines. That was a joke, sorry. That's an old format, don't worry about that. And it's not strict. That means all the debugging information's in there. Okay, it's a binary, but it's not a runnable binary. If we did a file on hello.s, it would say, oh, this is assembler source code and it's ASCII text. So the assembler translates the assembly into an object code. Now, we can't just run the object code. We could try, well, it'll say permission denied, but even if we gave it permission to run, let's cannot execute exec format error. He couldn't figure out what was going on there. So we still need to package it together to something that our operating system can run. And you use the linker for that. Normally use LD. Unfortunately, when I try and do LD on what's produced by GCC, it is a giant nightmare to put all the object codes together, because it's not just that object code, it's a bunch of other object code in order to get to run on a modern operating system. So I found out that you can just use GCC and it wraps it all together for you. Oops, hello, hello.o. And we do a file on hello. All right, ooh, it's a Pi executable, nice. Version 1, dynamically linked, there's the interpreter, etc., etc. All right, so now it is something that Linux can run. And then we will go ahead and run it, and there we go. So there are now, hopefully you see that there's extra steps. What's important to keep in mind is these extra steps of converting to assembly and then linking it together are required for pretty much virtually all languages. The assembly is where it actually translates your program language to a machine code format, and the linking is what packages it together so it can run on your hardware plus operating system. Now, some of you may observe that a microcontroller doesn't have an operating system. That's correct. You still have to link it because you have to make sure that the data is in the current addresses so the processor can still run it. So there's still linking involved. Just on a small microcontroller, there's just a lot less of it. But you still have to link. Okay, so the compiler converts it to assembly. The assembly is then converted to machine code and then packaged together so you can run. Now, we're not going to focus on the whole linking together and running on the operating system or through the kernel, because that's going to be covered in operating systems. We're going to be more concerned about assembly and actually using assembly and running it, because hopefully you can see how that assembly can run directly on our processor. Bless you. Again, all right, takeaways. The assembly is your interface between the program language and the hardware for your compiler, or that's the interface we are presenting as computer architects. The compiler spits out the assembly, and then we can run the assembly on our processor. So the assembler, we had AS, but we're going to stick with NASM. I think it's going to be a little more friendly, although it's going to have a couple of little tricks with it. Translates the assembly to machine code. The linker packages the machine code, so that the operating system can run your program. Again, every language has to assemble and link at some point. Now, it doesn't have to do that before it runs. A lot of modern languages, like Java, will actually assemble and link during runtime. That's okay, but it still had to do it at some point. Interpretive languages, of course, also do it at runtime as well. All right. Now, we should start talking a little bit about the syntax. We'll see how far I get. Well, actually, I will not get very far today, because it's going to be kind of painful. Because first off, you have to come up with what your syntax is going to be. If we're doing move reg1, reg2, well, what's going on here? Oh, so we have one person says we're moving contents of register 1 to register 2. Okay. Is there something else that could be going on?
You're setting 1 equal to 2.
Oh, okay. I see what you mean. Well, we are moving the contents of registers. And that's what this command does. But are we moving from register 1 to register 2, or are we moving from register 2 to register 1? Question. What? Oh, you go 1 to 2? Let me ask this question. Is it clear?
No.
Not at all. So in Intel version, you move from destination to source. AT&T, you move from source to destination. Or, yeah. Yes. Everyone got this. depending on what your assembler is, it may be one direction or the other direction. That is what is going on. Sorry, guys. How do you find out? You figure it out. I go online and hope something makes sense. IDA Pro, which, by the way, security people, if you want to make a ton of money, get really good at this program. Because this program takes a binary, just a binary, and it is a tool that finds all the functions inside the binary, and you can start using it to actually reverse engineer exactly what the program is doing. Because we don't have a disassembler that can take the binary and produce the language, the source code for it. But with IDA Pro, you can start piecing together the different functions that are inside of it, start labeling each one of it, and then IDA Pro will start helping you paste them all together, and eventually you'll be able to come up with what the final source code is. This is a great tool for security, because if you're trying to do the analysis of the security of a program, what better way than to look at the binary and find out where the vulnerabilities are there. It is a lot of work to become proficient at this. I have met people who are. It is actually wonderful to watch them work. It's like watching a really complex Sudoku puzzle being solved by a master. It's pretty cool. Well, anyways, that's what IDA Pro uses. Windows uses it as well. OpsJump and Unix prefer the other, although they don't stick to it either. So for the most part, I'm going to try and stick with the IDA Pro version just to make because I had to pick one. Also, how do we represent numbers? Well, binaries, you have ones and zeros. Well, that's kind of easy. Although in the Unix version, Intel and AT&T actually both allow this, aka in all versions, you can do 0B and say that this is going to be binary data. Or you can put a B at the end to say that it's a binary data. Wait, does that look familiar? I think Verilog did the first one, except it had a little apostrophe, single apostrophe between the B and the number. You can do the hexadecimal one. I definitely prefer the first one because it's easy to notice, but unfortunately you're going to see the second one a lot, and that's the H at the end. Which syntax should you use? Unfortunately, I just have to tell you, don't get stuck on the syntax. Figure out what syntax is being used and learn to live with it. Sorry, guy. I'm going to tell you right now, if you try and convert anything to one syntax or the other, it is going to drive you insane. Just, if the file is in this syntax, live with it and just deal with it. Be able to quickly identify syntax from existing code, that is a good point. And actually, once you get used to both, it's pretty easy. And then, unfortunately, each assembler is different. NASM, GNU, Intel, they're all going to be different. Sorry, guys. But if you want to get really good at assembly, you just need to practice, and it'll come to you eventually. These lectures assume traditional Intel syntax, which is basically IDA Pro versus NASM. All right, we have Hello World. Hey, doesn't this look a lot simpler already than the previous one? Well, let's go compile it real quick. I think I wrote it. I hope I did. So here it is up here. I'm going to open up my little make file. So I NASM FELF32. That means this is a 32-bit assembly. So generate 32-bit object code. Link it, LD, link it as a 32-bit, and then we'll run it down here. Hey, notice I didn't have to use GCC. I'm going to tell you right now, is with your assembly, as long as you don't try and use libc or some type of library, it's actually not that hard to write this assembly. But once you have to use a library, oh my goodness, it's going to become a nightmare when you start linking. By the way, printf is a library code, so you don't have printf or scanf or any of those functions. But we have ways around it, and we'll get to that. So I call make, and it automatically runs it for us. Notice that I called right here first, hello world. make report an error because our program actually returns that there's an error. That's just what it does right now. And we could fix that, but I haven't yet. Okay. So let's look at this code. We have section.text. What that means, the .text section of your assembly is your code. You put the code in the .text section of your assembly file. Global underscore start is saying that the label underscore start is something that's global that needs to be seen from outside of this assembly file. The reason why that's important is because underscore start is where the linker is going to look in order for your program to start. AKA when it packages it together so they can run on Linux, it'll say, hey look, your start point is where this label is. Well, how do you put a label? You have the start of it be the label name and then a colon. So your labeling start is right here. Where do we start? First thing we do, move EDX lit. So we're going to move LEN into the EDX register. Well, what's LEN? So we haven't figured that one out. So let's go ahead and jump down here. Section.data. If you wish to put any static data, you remember that from data structures where I was talking about your static, stack, and heap. This is where the static data goes. And that is called, you start with section.data. Notice the first thing is we label something called MSG, or message, not sodium glutamate, not that. No. Message, double byte, where you have hello world, comma, and then 0. Hey, what do you think this is?
Memory address?
No. Well, this says hello world, but when we print it out, what are we actually printing? We're not printing just hello world. This is tricky, but you have to think very literal.
The explanation point?
Okay, cool. We are printing out the exclamation point. That is correct, but the exclamation, yes. Remember, we're printing out a new line. So the exclamation point here, that's the new line. During the assembly, you have to be extremely, extremely precise. We're putting out hello world, exclamation point, and a new line. If you don't specify that, it's not going to happen. And this is basically just a way to say that len is equal to $-MSG, namely the length of this. So the assembler can automatically compute the length, because if you notice this is a static variable, it's not going to change in size, so it can compute the length. So what the assembler actually does is gets this data, figures out what the address of len is going to be inside your program, puts that address here so that when you do this move, it's going to read from that address, len, and put it into EDX. It's also going to read from MSG and put into ECX. It's actually going to read or have a pointer to that memory. It's not going to be the actual length itself. That's a little hard to see because it's kind of done for you, but notice that ECX is actually a pointer to message. All right, EBX is to 1, file descriptor, std out. In the Linux, so this program is only going to work in Linux because we're going to do a Linux system call. That means we're going to interface directly with the Linux kernel. And the way we do that is we have to set up the EBX is where, well, actually EAX, you set that to what function of the kernel you wish to call. We're going to call system write. And when you call system write, the next parameter in EBX is where you're writing it to. By convention in Linux, any file descriptor 1 is standard out, aka the terminal. So you say, you put EAX to be the system call you wish to call, EBX is what you're going to call it to. Notice that we set ECX to be the message and then EDX to be the length. That is how you do the syswrite system call inside of Linux. Let's see if we can do a man on that. That is not the right one. Let's do the correct man. If you look down here, we have file descriptor. File descriptor. We have a pointer. There's the pointer, ECX. And we have the size count, which is the length. That's EDX. So hopefully you can see how we can already translate how to make it this system call. We do the system call, which prints it out, and then we're going to move to the system call for system exit. It doesn't take any more parameters, so we just get out. Notice that int x0x80, that is saying send an interrupt to the processor, and the interrupt is we need to do a system call, so load the kernel. And then once it has the last interrupt, we haven't talked about interrupts too much in our processor, calls the kernel and says this program is done. Don't do anything more. All right. How are we doing? Okay. All right, fine, whatever. Sure. All right.
Just process it.
Just process it. All right. Hopefully you can see what's most important right now. Well, two things important is one, being able to write this assembly, because you are going to have assembler programs. But the other one is to see that, hey, look, since these are simple instructions, move this data here, move this data here, move this data here. We're not going to talk about interrupts, but just say interrupts are going to work, which is really, think of an interrupt right now as jump to this function. That's the easiest way to do it. And then interrupt again. So hopefully you can see how we can make a processor that could move data around, and then we'll just say there's a special kernel mode that can do the rest for us. All right. Let me pause.